Vectors got their origin in the first 2 decades of the 19th century when the complex numbers gained their geometric representation. Contributors like Argand, Carl Friedrich Gauss conceived of complex numbers as points in the two-dimensional plane, that is, as two-dimensional vectors. Later, mathematicians and scientists worked with vectors in various ways. A vector is a quantity that has both magnitude and size and a direction. Both of these properties must be given in order to specify a vector completely. Vectors represent any number of physical objects or phenomena. Wind, for instance, is a vectorial quantity because at any given location it has a direction such as northwest, a magnitude say 40 kilometers per hour. Vectors are an absolutely essential tool in physics and a very important part of mathematics. But their applications are not just restricted to these two fields. They are numerously used in almost all fields, be it economics, engineering, numerical methods, optimization, etc. In this module on Euclidean spaces and vectors, we introduce the concept of a vector as an n-tuple as well as a column vector, which in fact brings more relevance when we talk of applications of vectors in the field of economics. This enables us to make use of vectors using matrix theory, which in turn is seen applicable in numerous problems related to manufacturing, revenues and various other parameters on which decision maker focuses. Apart from this analytical aspect of vectors, we also give a brief idea of the geometry of vectors in the Euclidean space. A lot related to vectors depends on the linear dependence or independence with other vectors. So, this concept is seen in both analytical and geometrical type. An attempt has been made to associate various economic applications to the different concept of vectors and its related forms. After studying this module, you shall be able to know the concept of vectors and the algebraic operations associated with the vectors, the analytical and geometrical aspect of Euclidean space, vector space spanned by set of linearly independent vectors. Get an overview of the application of vectors and related topics in economics. A quantity having direction as well as magnitude, especially as determining the position of one point in space relative to another, is called a vector. So, vector is a symbol used to refer to an ordered set of variables or coefficients. Symbolically, a vector can be represented by v is equal to v1, v2, v3 up to vn, or v1, v2 down to vn, where where I varies from 1, 2, 3 to n, that can be variable or constant, are called the components or the coordinates of the vector v. Here vi is called the ith coordinate of the vector v. A vector having n components is referred to as n vector and has dimension n. The n vector 0, 0, 0 up to 0 is called the null vector. Geometrical interpretation. A vector v which is equal to v1, v2 in R square can be geometrically represented in the plane by a point which is at a distance of v1 units from 0, 0 in the x direction and at a distance of v2 units from 0, 0 in the y direction. Therefore, the movement in the plane can be uniquely determined by an ordered pair or a two vector v1, v2. The vector from the point P v1 v2 to the point Q u1 u2 is the displacement vector PQ u minus v1 comma u2 minus v2. This vector PQ is the directed line segment. In a similar way, three vectors represented by triplets of real numbers can be geometrically viewed using three mutually orthogonal coordinate axes, usually called the x-axis, y-axis, and z-axis. Likewise, an n vector has a corresponding interpretation, though no concrete geometry can be done in this case. Analytically, for n vectors, P v1 v2 to vn and q u1 u2 to un, displacement from point P to point Q is the vector pq given by pq is equal to u1 minus v1 comma u2 minus v2 right up to un minus vn. Economic interpretation of vectors. First, suppose a warehouse has n different commodities denoted by x1, x2 right up to xn. Daily, the number of units are A1, A2, AN of each commodity is recorded in the stock. Then it would be more convenient to represent these in an array form, which can be either a row or column. In this case, that is, as write up A1, A2 right up to AN, or A1, A2 right down to AN. There are the n tuples or the n vectors called the row vector or the column vector respectively. Suppose there are n consumers for m different commodities, say bread, tea, eggs. Then consumption of consumer C can be represented by m tuple given by C1, C2, Cm, where Ci represents the unit of the ith commodity consumed by consumer C. Euclidean space. Euclidean space denoted by e raised to the power of n consists of all ordered n tuples of real or complex numbers. Relating our study to real life application, we restrict ourselves to the field of real numbers R. So we take n-dimensional Euclidean space as Rn, which is the n-fold Cartesian product of R. N belongs to n. Hence, R consists of real numbers. R squares consist of ordered pairs, that is x1, x2. That is, R squared is equal to bracket open x1, x2, such that xi, x2 is belongs to R. Similarly, Rn consists of ordered pair x1, x2 right up to xn. That is, Rn is equal to x1, x2 right up to xn. That is, xi belongs to R, where I is equal to 1, 2 right up to n. As the vectors discussed have a geometric representation in the corresponding coordinate plane, so vectors can be thought of points with directed magnitude. Magnitude of a vector. If v is equal to v1, v2 right up to vn as an n vector, then its magnitude or length is denoted by p and is given by v, which is equal to under root v1 squared plus v2 squared right up to vn square. So v is called the Euclidean norm of v. Equality of vectors. Two vectors v and u is said to be equal if each of their corresponding components are equal. That is, v1, v2 right up to vn is equal to u1, u2 right up till un. If vi is equal to ui for all I is equal to 1, 2 right up till n. Scalar multiple of a vector. If v is equal to v1, v2 right up to vn is an n vector and k is a real number, then kv is called the scalar multiple of v by the scalar k. The scalar multiple kv is the n vector whose components are k times the corresponding components in v. That is, kv is equal to k bracket open v1, v2 right up to vn, which is equal to kv1, kv2 right up to kvn. For the geometrical interpretation, let us consider vectors in R square and let K belong to R. If we represent vector V by directed line segment starting from origin 0, 0 of the coordinate system, then for K greater than 0, KV is the vector in the same direction as V with length K times the length of V, and if K is less than 0, direction of KV is reversed and the length is multiplied by K. Addition of vectors. If v and u are two n vectors, then sum of v and u denoted by v plus u is the n vector obtained by adding each component of v to the corresponding component of u. V plus u is equal to v1, v2 right up to vn plus u1, u2 right up to un, which is equal to v1 plus u1 plus v2 plus u2 right up to vn plus un. Again, for the geometrical interpretation, we take vectors v and u in R squared as v is equal to v1, v2, and u is equal to u1, u2. Then vector v plus u is the diagonal of the parallelogram whose adjacent sides are v and u. Difference of vectors. If v and u are two n vectors, the difference of v and u denoted by v minus u is the n vector obtained by subtracting each component of u from the corresponding component of v. V minus u is equal to v1, v2 up to vn minus u1, u2 up to un, which is equal to v1 minus u1, v2 minus u2, vn minus un. In fact, v minus u is equal to v plus bracket open minus 1 u. Also, v minus u equal to 0 implies v equal to u. For the geometrical interpretation of differences of two vectors in R square, we add vectors minus u to v, That is, we take the diagonal of the parallelogram whose adjacent sides are v and minus u. Linear combination of vectors. If v and u are two n vectors and k and l are real numbers, then the vector kv plus lu is said to be a linear combination of v and u. That is, kv plus lu is equal to kv1 plus lu1, kv2 plus lu2, right up to kvn plus lun. More generally, if v1, v2 right up till vm are all n vectors and k1, k2 right up to kn are all real numbers, then the linear combination of vectors v1, v2 to vm is given by kv1 plus k2, v2 right up to kn, vn. Scalar product or dot product. Let v and u be any two n vectors, then the scalar product is defined as u into v, which is equal to u1 into v1 plus u2 into v2 plus u3 v3 right up to un into vn, which is equal to sigma I from 1 to n ui vi. For example, let C be equal to C1, C2, C3 to Cn be the cost components of n different commodities, and V is equal to V1, V2, V3 right up to Vn be the available commodity vector. Then the total value of commodity vector is C1, V1 plus C2, V2 right up to Cn, Vn. That is summation I from 1 to n Ci, Vi, which is equal to C into V. That is the scalar product of C and V. A finite set v1, v2 right up to vm of m vectors in Rn is said to be linearly dependent if any one of them can be expressed as a linear combination of the remaining vectors. On the other hand, if no vector in the set can be expressed as a linear combination of other vectors in the set, then the set of vectors is called linearly independent. Equivalently, a finite set v1, v2 to vm of m vectors in Rn is said to be linearly dependent if and only if there exists a set of scalars c1, c2, c3 right up to cm, not all 0, such that summation I from 1 to m ci vi is equal to 0. This is denoted by equation 1, where O represents the null vector of Rm. On the other hand, if 1 holds only when ci is equal to 0 for all I equal to 1, 2, 3 right up to m, then the vectors are said to be linearly independent. We now view the concept of linear dependence or independence in R squared in the figure. It can be seen that for the vector v is equal to 1, 2, the vector 2, v and minus v are linearly dependent. However, in figure, vector v is equal to 1, 2 and u equal to 2, 1 are linearly independent. Example, consider the set v1, v2, v3 in R raised to the power of 3, where v1 is equal to 1, 1, 2 into v2 is equal to 2, 1, 3, v3 is equal to 0, 1, 1. Clearly, 2v1 minus v2 is equal to v3. Therefore, v1, v2, v3 must be a linearly dependent set of vectors. Equivalently, using the mathematical definition given in 1, we need to determine scalars C1, C2, C3 such that C1 V1 plus C2 V2 plus C3 V3 is equal to 0. That is, C1 into 1, 1, 2 plus C2 into 2, 1, 3 plus C3 into 0, 1, 1 is equal to 0, 0, 0. That is, C1 plus 2C2 is equal to 0. C1 plus C2 plus C3 is equal to 0. 2c1 plus 3c2 plus c3 is equal to 0. Solving this system for c1, c2 and c3, we get c1 is equal to 2, c2 is equal to minus 1 and c3 is equal to minus 1. Since we get non-zero values for the scalars, therefore vectors v1, v2, v3 are linearly dependent. Remarks. First, any set containing the vector 0 is linearly dependent because for every non-zero scalar c, we have c into 0 equal to 0. Second, if a set of vectors is linearly dependent, then one of them can be expressed as linear combination of all other vectors in the set. This is because if c1 v1 plus c2 v2 plus c3 v3 is equal to 0, where at least one of the c1, c2, c3 is non-zero, say c1 is not equal to 0, then V1 is equal to minus 1 divided by C1 into C2 V2 plus C3 V3. Third, using the set of any two linearly independent vectors in say R square, if we consider its all possible linear combinations which could result in extending, shortening, reversing the given vectors, combining the vectors using parallelogram law. This would thus generate an infinite set of vectors which will exhaust all the vectors in R squared. 4. Any set of 3 or more vectors in R squared must be linearly dependent. The set of all linear combinations of n linearly independent vectors in R raised to the power of n constitutes the n-dimensional vector space R raised to the power of n. Let V be a vector space and let S be equal to V1, V2, V3 up to Vn be its subset. Then S spans or generates V if every vector small v belongs to capital V can be written as a linear combination of vectors in S. That is, there exists scalars C1, C2, C3 up to Sn subject to V is equal to C1, V1 plus C2, V2 right up to Cn, Vn. Here S is called the spanning set of vector space V. For example, S is equal to 1, comma 1, comma 0, comma 0, 1, 0, comma 0, 0, 1 spans the vector space R cube as any vector V is equal to x, y, z in R cube can be written as a linear combination of vectors of S as x into 1, 1, 0 plus y minus x into 0, 1, 0 plus z into 0, 0, 1 is equal to x, y, z. This can be illustrated as follows. Here we need to determine the scalars C1, C2 right up to Cn such that C1 in bracket 1, 1, 0 plus C2 0, 1, 0 plus C3 0, 0, 1 is equal to x, y, z, or 1, 0, 0, 1, 1, 0, 0, 0, 1 into C1, C2, C3 is equal to x, y, z. Since the coefficient matrix of the system has non-zero determinant, the system must possess a unique solution. Using elementary row operations, it can be checked that the solution of the system is given by x, y minus x, z. Note for the spanning set phi, the vector space is 0. Let V equal to V1, V2, V3 up to Vn and U be equal to U1, U2, U3 to Un be two vectors. The straight line I passing through this point is given by x is equal to 1 minus t into v plus tu, where t is a real number and x is equal to x1, x2, x3 is a point on line I. Similarly, in the line I through V, which is equal to V1, V2, V3 to Vn, and U is equal to U1, U2 up to Un, is the set of all x, which is equal to x1, x2, x3 right up to xn, such that x is equal to 1 minus t into V plus Tu, where t belongs to R. We now introduce the equation of a plane. Let P be a plane in R cube passing through V, which is equal to V1, V2, V3, and N, which is equal to N1, N2, N3, which is not equal to 0, 0, 0, orthogonal to it. Here N is said to be normal to plane P, as N is orthogonal to any line in the plane, which is equal to x1 into x2 into x3, a point in R cube. Equation of plane can be determined by using the fact that the normal vector n must be orthogonal to every line in the plane P, say through x, and then n into bracket open v minus x bracket close is equal to 0 represents the equation of the plane. Similarly, in Rn, a hyperplane through V equal to V1, V2, V3 up to Vn, orthogonal to vector n, which is equal to n1, n2, n3 right up to n, which is not equal to 0, 0, 0, is the set of all points x equal to x1, x2, x3 right up to xn, satisfying n into x minus v equal to 0. We now discuss the concept of lines and planes in terms of linear span. Suppose we have three non-zero vectors in R cube. We consider the following three possible cases. Case 1, all three vectors are parallel. Then geometrically, all three vectors lie on either side of the same line joining the origin. More mathematically, all three vectors are scalar multiplication of each other. And so any linear combination of these vectors is also a scalar multiple of each. Hence, their span must be the vectors along the line through the origin containing these three vectors. That is, if u, v, and w are vectors such that s is equal to u, v, w, comma, v is equal to alpha u, and W is equal to beta U, where alpha and beta are scalars, then span S is equal to mu U, that is mu is a scalar, is the dotted line through the origin. Case 2. Two of the three vectors are not parallel, but all three are coplanar. That is, they lie on the same plane. Here, some third vector is in the plane as well. So it must be a linear combination of the first two. So span for three vectors is the same as span of the first two vectors. That is the set of all vectors in the plane containing all the three vectors. Case 3. All three vectors are non-coplanar. We know two non-parallel vectors in R square generate the space R square, which can be seen using parallelogram law. Similarly, in R cube, we can construct the parallel piped with edges parallel to three given vectors, and their sum would be represented by the diagonal of the parallelly piped. Now, the span of these three vectors will be then whole of R cube. Suppose a manufacturing unit has a capital of M units available for the production of N different commodities whose costs of manufacturing per unit are C1, C2, C3, right up to Cn respectively. Now the commodity vector is X is equal to X1, X2, X3, right up to Xn, enables us to determine the number of units of each commodity Xi to be manufactured so that the budget inequality holds. This is given by C1 x1 plus C2 x2 right up to Cn xn, which is less than equal to m, which is known as equation 2. Relating with the notion of lines and plane done above, we see that when equality is satisfied, then it represents the equation of a hyperplane whose normal is the cost vector C1, C2 right up to Cn, and xi greater than equal to 0 for all I. A fruit vendor sells 5 kgs of apple, 3 kgs of kiwis, and 8 kgs of pears on a particular day. Suppose the price per kg at which he sells his fruit are 90, rupees 150, and rupees 75 for apples, kiwis, and pears respectively. Then the price vector P is given by 90, 150, 75, and the quantity vector Q is given by 5, 3, 4. Now the money in cash by him at the end of the day is given by 5 into 90 plus 3 into 150 plus 4 into 75, which is equal to 5, 3, 4, 90, 150, 75, which is equal to Q into P, which is the scalar or the dot product of the price vector and the quantity vector. Let us summarize what we have learnt in this module. A vector can be represented by V, which is equal to V1, V2, V3 right up to Vn, or V1, V2 down to Vn, where Vi's I is equal to 1, 2, 3 right up to n, that can be variable or constant or are called the components or the coordinates of the vector V. Euclidean space denoted by e raised to the power of n consists of all ordered n tuples of real or complex number. N-dimensional Euclidean space Rn is the n-fold Cartesian product of R, where n is a part of n given by r raised to the power of n is equal to x1, x2 right up to xn, where xi is part of r, where I is equal to 1, 2 right up to n. The magnitude of a vector is given by the under root of v1 squared plus v2 squared right up to vn squared. The equality of vectors is equal to v1, v2 right up to vn, which is equal to u1, u2 right up to un if vi is equal to ui for all I equal to 1, 2 right up to n. The sum is v plus u, which is equal to v1, v2 right up to vn plus u1, u2 right up to un, which is equal to v1 plus u1, v2 plus u2 right up to vn plus un. Difference of vectors. U is equal to v1, v2 right up to vn minus u1, u2 right up to un, which is equal to v1 minus u1, v2 minus u2 right up to vn minus un. Linear combination of vectors. Kv plus Lu is equal to Kv1 plus Lu1, Kv2 plus Lu2, which goes up to Kvn plus Lun. Scalar product U V is equal to U1 V1 plus U2 V2 plus U3 V3 right up to Un Vn, which is equal to summation I from 1 to n Ui Vi. A finite set V1, V2 to Vm of m vectors in Rn is said to be linearly dependent if and only if there exists a set of scalars C1, C2, C3 up to Cn, not all 0, such that summation I from 1 to m Ci Vi is equal to 0, where 0 represents the null vector of Rm, and if Ci is equal to 0 for all I equal to 1, 2, 3 till m, then the vectors are said to be linearly independent. The set of all linear combinations of n linearly independent vectors in Rn constitutes the n-dimensional vector space Rn. The straight line 1 or L passing through these points is given by x is equal to 1 minus t into v plus tu, where t is a real number and x is equal to x1, x2, x3 is a point on line 1, a hyperplane through v is equal to v1, v2, v3 to vn, orthogonal to vector n is equal to n1, n2, n3 till nn, which is not equal to 0, 0, 0 is the set of all points x equal to x1, x2, x3 right up to xn, satisfying n into x minus v equal to 0.